Okay, so one of my favourite ideas in category theory is the idea of a universal morphism. And that's because most of the important constructions in category theory correspond to universal morphisms. Things like products, coproducts, exponential objects, equalizers, co-equalizers, can extensions, natural number objects, etc., etc. They're all examples of universal morphisms. And I think universal morphisms are great. And I did a video on universal properties where I defined them. But there's actually a more intuitive way, I think, of understanding what universal morphisms really are. And it's such a deep concept. I mean, when you look at universal morphisms, there are so many kind of structures and interesting things which exist in general around universal morphisms. And then when we look at all these special cases, like the ones I just listed, you can see examples of all these sort of interesting entities which we know are there from the general theory of universal morphisms. Okay, so I don't get as much chance to make videos these days as I used to. I'm much more busy with work. And so when I do make these videos on category theory, I really like to pick the type of topics that I think are most important. And I think that this one today on representable functors and universal morphisms is super important, and I'm going to be running with a particular example, but I thought I should just say something about the many other cases that the kind of topics we're going to cover today can be applied to. So let me talk about a few functors. So firstly, we can think about the category of groups. Now, I haven't really defined the category of groups in this series of videos, and if you don't know what it is, don't worry, it won't come up again in this video, but it turns out that there's a forgetful functor from the category of groups to the category of sets. So basically, the category of groups has objects as groups, and we can take a group and we can just take the elements from that group. And that's what this forgetful functor does. Okay, here's another functor. This one takes vector spaces and it forgets the structure of the vector space and just returns the elements. It's another forgetful functor. There's another kind of functor like this that takes a topological space and it forgets about the topological structure and just gives the set of points. There's another forgetful functor which takes a graph and it just returns the set of edges of that graph. So these are all forgetful functors, and the ideas I'm going to talk about today can be applied to any of these situations and many more. And in each case, we're going to be able to create the kind of left adjoint of this functor using the ideas I'm going to talk about today. Well, we're going to understand that. We're going to understand how we can think about these situations in terms of representable functors. And I think that's really the gold here, because that's really a very general and I'd say a very kind of appropriate way to look at these kind of situations. And yes, I mean, this is the idea. I mean, I could get quite carried away talking about how fond I am of the results we're going to discuss today. I mean, it almost seems as though we're looking at the kind of cosmic machinery which lies behind all of these different situations in mathematics. And in a way, we're looking at the kind of underpinnings of adjoint functors which occur everywhere in maths. So what I want to do is to try and make this idea of universal morphisms as natural as possible by looking at the idea in a certain way. And the central kind of tool that we're going to use is the Hom functor. So here we have part of a category which we'll call scripty A, and it has this object A here. And let's ask ourselves a question. What does this category look like from the perspective of A? And we can really answer this question with a Hom functor. So the idea of this is that we have this blank here, and we can fill in this blank with an object. For example, we could have the object B, and then this here is going to give us the set of arrows from A to B. So basically, the way that this category looks like from A's perspective, we can think of that as corresponding to the things that this A guy here could relate to. And so we could vary the different objects and think about the set of ways that A has of relating first to this object B, and it has these three arrows, these three ways that A can relate to B. But then we could change the object and we get this set of arrows, this set of ways that A can relate to C, and so on. And this information is encoded in this Hom functor. So this Hom functor really kind of tells us what the category scripty A looks like from A's perspective. And basically, Hom functors are going to be our tool to understand what universal morphisms are. And that's basically because if we have a functor, let's say a functor R from A to B, and then we want to talk about universal morphisms related to that, well, basically what we want to do is we want to compare the way stuff looks like from the perspective of objects in A with the way stuff looks like from the perspective of certain objects in B. And so what we're really doing is we're comparing Hom functors. Now, if you remember the definition of adjoint functors in terms of Hom functors, you're basically saying, oh, I have these Hom functors and they're isomorphic. And that's like a way you can define what adjoint functors are. And basically that formula, we're going to see where that formula comes from today by looking at universal morphisms in terms of Hom functors. And the basic idea is that if you have a functor into set, it might be isomorphic to a Hom functor, and if it is, it's called a representable functor. Let's go. So let's start with a kind of running example that we're going to look at, and that's the category of dynamical systems. So what's a dynamical system? Basically for us, it's just going to be a set of points, so maybe A, B, and C, and then there's an update function, which is a function from this set to itself. So maybe it sends A to B, and it sends B to C, and it sends C to B. So our dynamical system consists of a set X, in this case A, B, and C, together with a function from X to itself, which we could call U. And in this case, this is this function which sends A to B, B to C, and C to B. That would be U. So, generally then, a dynamical system, you could think of it basically as being what you might call an endo function, a function from a set to itself. And we have this category of dynamical systems, which I shall write like this. And the objects in this category consist of pairs of a set X and a function U from X to itself, and then a morphism, or an arrow, from one dynamical system to another one, X dash comma U dash. A morphism F is just going to be a function from X to X dash, which makes this kind of square commute. So basically, if we update first and then we apply the morphism, that's equivalent to applying the morphism first and then updating. And so there we are. Now I'm writing the category of dynamical systems like this, and that's because there's another way to think of it. If you see my video on graphs and dynamical systems, I go through this, but basically another way you can think of this category of dynamical systems is it's the category of functors from the free monoid with one generator, considered as a one object category. So basically here I'm talking about the category that has a single object, and of course that has an identity arrow. But in addition, we have these extra arrows. So there's sigma, there's sigma squared, that's sigma after sigma, and then there's sigma cubed, and so on forever. So this is just sort of free composition of sigma with itself, and we get all the things that we can make that way, and we don't identify any of them with each other. So it's a free monoid essentially, with one generator, sigma. Well, basically, if we denote this category here as this little loop here, then we can think of this category of dynamical systems as the category of functors from this free monoid with one generator to the category set. So the objects, these dynamical systems, they correspond to functors from here to set, and then these morphisms correspond to the natural transformations between such functors. So there we have it. That's our category of dynamical systems. This is what's going to be our sort of working example throughout this video. Now, there's a particular pretty simple functor that we're going to focus on, and it's the functor that goes from this category of dynamical systems to the category set, and we're going to call it R. And basically this is the forgetful functor. Okay, so it's a very simple idea. Basically the idea is just that we can take a dynamical system, and this functor R is going to send it to its set of states. So it's as simple as that. So when we operate this functor on a dynamical system, we get the set of states of that dynamical system. And when we operate this functor on a morphism between dynamical systems, we just get that morphism back, but we just think of it as a function between sets, which is what it's built out of anyway. So R basically just forgets about the update functions. And it's a pretty simple kind of thing. Now, basically the way I'm going to go with this video is I'm going to build up to calculating the left adjoint to this functor. Okay, so it turns out that this functor R here, this forgetful functor, has a left adjoint, which we could call L. We could even call it a free functor if we like. And we're going to figure out what that is. It's maybe not so hard to calculate the left adjoint. The point really, I suppose, is the method that I want to show you, because it's a very general method. Okay, basically, I'm using this example of dynamical systems so that we have something concrete to point to, but the method I'm going to use is very, very general, and it can be applied to lots and lots of situations. Okay, so here comes the sort of 5-minute recap of what Hom functors are. Now, I mean, to be honest, I think one should have some amount of familiarity with Hom functors and the Yoneda lemma to understand this video. Now, I'll try and briefly kind of recap the necessary things, but you know, if this stuff's unfamiliar to you, I recommend having a look at my video on the Yoneda lemma. Anyway, suppose we have a category A, and we have, and I'll call it scripty A, and we have an object capital A of scripty A. Now, if we have those things, we can form a Hom functor. And I've been writing this kind of thing like this previously, hom of a comma blank. I'm going to use a bit of different notation today, and I'm going to use this notation scripty a of a comma blank because I think it's more expressive. But anyway, the point of this functor is, let's say we have an object C in our category A, in our category scripty A. Well, this hom functor here is going to send this object C to this set of arrows from A to C. That's a set. So that's an object of the category set. What happens to an arrow, F, in the category scripty A? Well, that gets sent to this function here that I'm going to write as scripty A of A comma F. Okay, so basically the way that this works is that it's going to be a function from this set of arrows from A to C, which incidentally we could write as hom A comma C in the old notation, but I won't be using that notation today. Anyway, the point of this is that this function here is going to send an arrow K from A to C to the arrow F after K, which goes from A to D. And that's it. That's how this hom functor works. And hom functors are absolutely central to what we're going to be thinking about today. And using this idea of hom functors, now we can define what it means. And using this idea of hom functors, now we can define representable functors. So, okay, what is a representable functor? Well, let's consider this case here, where we have some functor from our category A to our category set. And if you want to keep a concrete example in mind, you might think of A as our category of dynamical systems, but you don't have to. Right, so it's functors like this that go into set, which might be what people call representable. And so when is a functor that goes into set representable? Well, the definition is a functor into set is representable if and only if it's naturally isomorphic to a hom functor. Okay, so this might seem a bit peculiar at first glance, but it turns out that representable functors are really, really central to mathematics in general. And basically, they give you, in my opinion, a sort of more intuitive way of looking at lots of the other things that happen in category theory. So basically, the idea is that when R is representable, that means that we're going to have an object A in our category scripty A, such that this hom functor, scripty A of A comma blank, is naturally isomorphic to this category R. So a way you can think of this is think about, say, the category of functors from scripty A to set, then this hom functor and R are going to be objects of that category. And the idea is that there should be an isomorphism from one to the other, and we call that isomorphism phi. So phi is just a natural transformation from this hom functor here to R, but it's a natural transformation which is an isomorphism. Okay, so there should be an inverse of this. And I'm denoting that this is an isomorphism using this tilde, this twiddle symbol here, which denotes that this arrow here, this 2-cell, is actually a isomorphism. Okay, so when R is a representable functor, well, that means that we can find this object A and this natural isomorphism phi. And in that case, we think of A, sometimes we call it the representing object, and that together with our natural isomorphism forms what we might call a representation of this functor R. Okay, so this is just terminology so far. So let's think about this practically. Okay, what does this mean for our example? Remember, we have this example where scripty A is the category of dynamical systems, and we have this forgetful functor from that to set. Now, is that a representable functor? Well, it turns out that it is. Okay, so there's a certain dynamical system which we might call n, s. Now, n here is the set of natural numbers, so the states of this dynamical system are these natural numbers 0, 1, 2, and so on forever. And then the update function s is just the successor function. So the successor of 0 is 1, the successor of 1 is 2, and so on. And so this is what this dynamical system n, s looks like. And I'll call this the natural numbers dynamical system. Okay, so it's basically, like I just think of it visually, it's just like a great big long line, and then each state just moves one step to the right when we do an update. Okay, so it turns out that if we have this as our object capital A, so that's an object in our category scripty A, which now in this example we're thinking of as our category of dynamical systems. Well, in this case, if we consider the hom functor, scripty A of A comma blank, what is this? Well, basically, this is going to take, say, an object C, and it's going to give us the set of morphisms of dynamical systems from this natural number dynamical system to the dynamical system C. All right, so let's look at an example. Let's suppose that C is this dynamical system. So then we can ask ourselves, what does it mean to have a morphism from this dynamical system here, this natural numbers dynamical system, to this dynamical system here, which actually I'll call it D, so I don't get confused with the letters. Okay, so basically what we're interested in here now is what is the set of morphisms of dynamical systems from our natural numbers dynamical system to this dynamical system. Okay, let me just clean up my notation a bit because this is getting confusing. Let's think of this dynamical system here. We'll say its set of states is D, and we have this update function U. And here we've got this special dynamical system with a set of states as natural numbers and the update function as a successor function. And what we're interested in is, in this category of dynamical systems, what's the set of arrows from our natural number dynamical system to this other dynamical system D with its update function U. So now here's the point. We can send this point 0 here anywhere we like. So we could send it here, but once we do that, the nature of morphisms of dynamical systems forces the rest of the things that happen, because we always have to have that the image of the update equals the update of the image. So in other words, we know that if we're going to update 0, then we know we get to here, and we know that has to go somewhere. But we know that that somewhere has to be the same place as where we get to if we apply our morphism and then we apply our update. So we know that 1 has to get sent here, and then we know that 2 has to get sent here, and then 3 has to get sent here, and then 4 has to get sent here, and so on. So the way that the rest of the kind of morphism works is forced if we know where 0 gets sent by this kind of arrow F from our natural numbers dynamical system to D, our element here of this kind of set of morphisms from this to this. So what I'm trying to convince you of basically is that the morphisms from here to our dynamical system correspond exactly to the states of this dynamical system here that's our target. In other words, this set here of morphisms is isomorphic to the set of states of our dynamical system D. And that's always going to be the case. And what is this set of states D? Well, it's basically what we get when we apply our forgetful functor R to the dynamical system D, U. So let me say this another way. Let's think about our category of dynamical systems. So I'll just write that in the full way like this. Now, let's suppose we have some dynamical system X, so some object in this category of dynamical systems. And we have this forgetful functor R, which sends dynamical systems to sets. And what we're interested in is applying our forgetful functor R to this dynamical system X. Well, it turns out that basically what we get from that is going to be isomorphic to what we get when we apply our hom functor. So let me just write this category of dynamical systems as scripty A, just to abbreviate it. So what I'm saying is that what we get when we apply our forgetful functor R to this dynamical system X is going to be the set of states of the dynamical system X, and that's going to be isomorphic to what we get when we apply this hom functor using the representing object, which is our natural numbers dynamical system, and we apply that hom functor scripty A of n comma blank to this object X. Or in other words, what I'm basically trying to say is that the set of things we get by taking the dynamical system X and forgetting about its update function is going to be isomorphic to the set of morphisms from our natural numbers dynamical system to X. Or in other words, more simply, the set of states of this dynamical system X corresponds precisely to the set of morphisms from this natural numbers dynamical system into X. So this natural numbers dynamical system seems really special. It's kind of like a sort of particle accelerator or something that can like throw beams into other objects in this category of dynamical systems to discover their structure in some sense. It's like, it reminds me of when they were discovering the structure of the atom, and they used these kind of machines to fire particles into things to discover their structure. Well, in a similar way, the kind of morphisms that come out of this dynamical system, the natural numbers dynamical system, correspond to the states of the target of those morphisms. And there are deep reasons for this. If you see the video on the Yoneda lemma, you'll see actually the reason why this works is basically because this natural numbers dynamical system itself corresponds to a hom functor. But that's a different way of applying the Yoneda lemma, not exactly what I want to do today. Anyway, the point here, what I'm trying to argue, is that in this case where scripty A is our category of dynamical systems, and we have this functor R, which is our forgetful functor that goes into set, in this case, this functor R is representable. And in particular, if we pick this object of our category of dynamical systems, which is this natural numbers dynamical system, then the hom functor associated with that is going to be naturally isomorphic to our representable functor R. So this is going to be a natural isomorphism. So how is it that this natural isomorphism here works, this phi? Well, it's firstly there's a natural transformation phi from this Hom functor here to R, and then for every dynamical system, d comma u, there's going to be a d comma u component of this natural transformation, and that's going to be a function which goes from the set of morphisms from our natural number dynamical system to d comma u. It goes from those kind of things to what we get when we apply our forgetful functor R to d comma u. So this is the sort of signature of a component of this natural transformation. It basically sends these kind of morphisms of dynamical systems to states of the target dynamical system. How's it work? Well, it's going to send a morphism f to f of 0, which is going to be the sort of state of our dynamical system, our target dynamical system, which corresponds to that map from the natural numbers dynamical system. And we can kind of see that, yes, this is going to be a natural isomorphism, because we've seen that if we sort of try and go the other way around, if we just pick an element of the set of states of our dynamical system here, then there's only going to be one morphism from our natural number dynamical system to that thing which sends the 0 on top of that state. So we've seen this kind of thing with this sort of visual argument, but of course you can prove this more rigorously. Okay, so we've got this basic idea of representable functors under our belt now. Now we're going to have a bit of a jump in abstraction, because we want to understand comma categories. And this is going to help us later. So just before I go over comma categories, I mean, I've covered them in other videos, but I think it's important to have this kind of higher vantage point to look at things from. I should say there's a few abstract notions coming up in this video now, and you know, if it starts to get unclear, I give my usual advice, which is to put the video on double speed and watch the whole thing, because you'll see that there are lots of different inroads to these ideas. So if, for example, comma categories seem unfamiliar to you, there's other ways to look at the thing from other perspectives, and then you can understand comma categories coming from a different direction. Anyway, before I go over the definition of comma categories, let me kind of tell you the punchline, so you can see where this is going. So we want to define something called the category of elements. So we have a situation where we have a category A and we have a functor R, which goes from A to the category set. And here's a nice simple example. A is just this category of two objects and this arrow G and identity arrows, which I'm not drawing. And then we have this functor R, which takes that stuff into set. So these objects here become these sets, and this arrow G here gets sent to this function R of G. So this is a functor which goes into set. So we can think of it as this sort of diagram in set, where we have these sets and these functions, and we can draw these in the usual way. So, you know, we draw these kind of bubbles of points and these kind of threads showing how our functions work. And then the idea to convert this into the elements category is basically just that we rub out some of these bubbles. So I'll do it here actually. So if we just sort of rub out these bubbles, and then we label these with the kind of objects of scripty A that they're associated with. So these sort of come from A, and this comes from A dash. And then we can label these arrows. We'll call this arrow G. We'll call this arrow G as well. We won't get confused because these arrows have different domains. And this is basically our category of elements. So basically the kind of slogan here is that the category of elements is what you get when you draw a diagram in the category sets. So you have these sets drawn as bubbles of points, and then you just rub out the bubbles. Basically, that's what a category of elements is. Oh, this should be an A dash here. This is associated with this object here. Right. Anyway, if that's unclear, that's understandable because I haven't really defined what I've been talking about. But anyway, this is basically the idea of the elements category, which we could write as integral AR, or some people would call it EL of R, the elements category of R. We're going to get to this more precisely very shortly. I'll just say another way we can write this, actually my preferred way, is we can write it as the comma category, using a singleton set and R. And this is the reason I want to talk about comma categories now. So let me go over the idea of comma categories, and then we'll get back to this notion of the category of elements in a more precise way. So, comma categories are just amazing, in my opinion. There's a lot of things in category theory involving universal properties that can seem kind of really abstract, and comma categories usually give you a way to have these kind of concrete instantiations of things where, rather than just having these kind of, oh, for all of this there exists a unique that such that blah blah blah, we can form these sort of comma categories, and then we just say stuff like, well, we're talking about an initial object of this comma category or a terminal object of that comma category. And that amounts to saying the same thing as our universal properties say. So basically, comma categories are very general structures that can encode all sorts of things that we're interested in and give us a really easy way to think about universal morphisms. So, definition of a comma category then in general. We have categories Q, B, and A. We have a functor G from Q to B, a functor R from A to B. And then we can write this, we can define this comma category. And I'm going to write this today as G slice R. You can also write it as G downwards arrow R. And that's notation that I was using in some previous videos, but now I sort of prefer this slice notation. Anyway, what is this comma category? Well, I'll tell you what its objects are and what its arrows are. So what are the objects of the comma category? Well, they consist of triples of an object Q of scripty Q and an object A of scripty A and an arrow from where Q goes under G to where A goes under R. And that arrow, let's call it H. So it's these triples that constitute the objects of our comma category. Okay, what are the arrows? Well, an arrow from this object here, QHA, to this object here, Q-H-A-, consists of a pair of an arrow U from Q to Q-, so that's going to be an arrow in scripty Q, and this arrow V from A to A-, that's going to be an arrow in scripty A. And we require that those two arrows make this sort of diagram commute. Okay, so if we do H and then RV, we get the same thing as if we do GU and then H-. And that's it. That's the definition of a comma category. You compose arrows by composing them sort of just component-wise, as you'd expect. And if I'm going over this too fast, you can look at my video on universal properties, or also my video on can extensions, and I go over comma categories more slowly in those videos. Actually, you know, if a lot of this stuff does seem unclear, that video on universal properties might come in very useful. Anyway, we're going to be using comma categories today, and what I want to do with them right now is to show you that the elements category can actually be thought of as a special kind of comma category. So this is the sort of general setup for a comma category, and now I want to look at a special case. So for our category Q here, we're going to have this terminal category that I write as 1. This is the category that just has a single object, and the only arrow is the identity arrow. And then for our category B, we're going to use the category set. And so then this, and for our functor G, we're going to use this functor that sends our single object category 1 here to the singleton set. So this is just a fancy way of saying we're going to pick out the singleton set. So the set with a single element called star is an object in the category set, and a way we can pick out an object in a category is with a functor from this terminal category. So this denotes the functor which just picks out our singleton set. And so when we have this sort of setup here, we have these two functors, this one that picks out the singleton set and this other functor R. And so we can form the comma category, singleton set slice R. And it turns out that that's precisely the same thing as the category of elements of R. And here's a more kind of direct way of defining this category of elements. So the objects consist of pairs of an object capital A in scripty A and an element little a of R of capital A, and then an arrow from one element little a to another element little a dash is just going to correspond to an arrow G from the object A to the object A dash in the category scripty A, such that R of G is going to send this little a to this little a dash. Okay, and that basically gives you this sort of the elements categories look like as I described before. Like I say, the slogan is get a diagram in set and rub out the bubbles around the sets. It's basically what an elements category is. Okay, so another very interesting thing about these elements categories is that they always come with these sort of projection functors. So basically the projection functor works like I'm writing here. So the idea is that all the kind of objects in this elements category are all sort of indexed with objects of scripty A. And then if we just sort of rub out the elements and keep the indexes, this gives us this kind of projection functor, which sends us from the kind of elements category back to the original diagram that we used. Okay, so why am I talking about elements? Well, there's a very, very interesting connection here between the representable functors and the elements category. And it involves the Yoneda lemma. I'm going to go over the Yoneda lemma again momentarily, but I thought a nice way to motivate this is just to sort of show you the result, which might seem a bit mysterious at this point, and hopefully it'll become more clear when we look at things in a more general way. So we've been thinking about representable functors. So suppose R is a representable functor. So that means we have this natural isomorphism here from this Hom functor to R. So we could say then that this phi here is a natural transformation from this Hom functor to this other functor R. Turns out that it's a natural isomorphism, but for the moment we'll just think about how it's a natural transformation. Well, that means we can apply the Yoneda lemma, and that means that corresponding to this natural transformation, there's going to be this element of R of capital A, and we'll call that element phi bar. Now I'll go over how the Yoneda lemma works again momentarily, but the point is that let's have a look at what this means in the kind of dynamical systems example that we've been playing around with. Okay, so remember, this is the case where scripty A is the category of dynamical systems, capital A is our natural numbers dynamical system, and R is our forgetful functor. So what does this look like in this case? Well, basically, we have this kind of picture. And in this case, it turns out, as we'll get to later, that the element of R of A, or basically R is the forgetful functor, A is our natural numbers dynamical system, so R of A in this case is just the set of natural numbers. And it turns out that the kind of element of R of A, which corresponds to this natural transformation here, it turns out that this is actually the special element of our natural numbers, which is 0. Okay? I think this is really interesting. Why is it that the Yoneda lemma is giving us this special natural number 0? And more interesting, much more interesting, is that it turns out that if we take our dynamical system of natural numbers together with this 0 here, it turns out that that is an initial object of the category of elements of our forgetful functor. Okay, so this is kind of crazy, right? It's like, why is it that this massive elements category has this kind of 0 thing as its initial object? Why should that be the case? And in fact, this kind of stuff works more generally. So more generally then, if we have this sort of more general case where we have a representable functor R from A to set, and then we find the element corresponding to that under the Yoneda lemma, then it turns out that in general, we're going to have the A and that kind of phi bar thing is going to be an initial object of the elements category of R. So this works generally for representable functors. Now, what I just said is quite a big jump in abstraction, and it might be difficult to follow. So what we're going to do now is we're going to have another sort of recap of how the Yoneda lemma works. And after we've done that, we're going to look at what's happening more generally. So it turns out that what I'm showing you here is only really the tip of the iceberg. There's a more general result that this is a special case of. And that general result basically allows you to understand any universal morphism in terms of these representable functors. Okay, so this is a kind of crazy result, right? Like R is this forgetful functor from dynamical systems to set. When we get the elements category of R, basically you can visualize that by thinking, well, we draw all the dynamical systems together, and we look at all of the kind of morphisms between the dynamical systems, and we imagine we have all these threads between different states showing us how these different morphisms of dynamical systems map these different states in different cases. And then we obliterate the boundaries of all the dynamical systems and think of that whole thing as like a giant category in its own right. That's the elements category. And then it turns out that the natural numbers dynamical system with its 0 is going to be the initial object of that structure. Okay, so this is like really very, very, very kind of complex in a sense. And it turns out that, this is just a special case of something that's so much more general. And this is what I'm going to get onto now. So before we get onto it, let's just have a brief recap of the Yoneda lemma, sort of 5-minute refresher. So basically the idea of the Yoneda lemma is that if we have a functor R from a category A to set, then we always have these kind of natural isomorphisms. So if we pick an object capital A, then the natural transformations from the Hom functor to R are in one-to-one correspondence with the elements of R of A. And this one-to-one correspondence is natural in both capital A and capital R. That's the Yoneda lemma. So we can sort of write it more, I prefer this way of writing it. So I use these double horizontal lines here to represent that stuff above the line is in one-to-one correspondence with stuff below the line. Now, for now, I'm not assuming that phi is an isomorphism, just a natural transformation from this Hom functor here to R. So how does this correspondence work? If we have a natural transformation upstairs, how do we get this element downstairs? Well, that's pretty easy. Basically, phi bar is just the 8th component of phi working on the identity arrow of A. Okay, because we know that the 8th component of phi goes from scripty A of A comma A to R of A. We know that the identity arrow of A is in here. So we can operate this on this, and this gives us phi bar. How does it work the other way around? Well, basically, this is the diagram that you draw over and over again when you're thinking about the Yoneda lemma. It's like this. So we want phi to be a natural transformation from this Hom functor to R. So we want squares like this to commute. And actually the fact that this square has to commute forces the nature of phi to have a particular form. So the way we can see this is we know that this thing at the top left has this identity element, identity arrow as an element. If we do phi of A on that, we get phi of A of identity of A. I mean, let's suppose what we're doing here is, let's suppose we know the nature of this phi bar and we're interested in, what's the phi that it corresponds with. So we know then that this should be equal to phi bar. And then what we're going to have down here is going to be R of K of phi bar. Now going this way around the square, here we get K, because we're sort of lifting this arrow K from A to A dash under these different functors, the Hom functor and R. And then what we have is that this should be equal to phi of A dash of K. And so what this is telling us in general is that for any arrow K from A to A dash, we should have that phi of A dash of K is equal to this. Now, if you think about it, this is basically telling us the nature of this function phi of A dash. If we know phi bar, then we can calculate how phi of A dash should work on this general element K using this formula. And so this defines how phi of A dash works. It defines this function phi of A dash for all its possible inputs k. And this works for a general a dash. So this defines exactly how phi should work. And so that's how you can go. If you have this and you want to get this, that's how you get it. So that's the Yoneda lemma in a nutshell. Now, drum roll, here is the big result that I've been sort of working up to. This is the very general kind of result, which, yeah, I think is just great. So here it is. So the setup. We're going to suppose we have a functor R from A to B, and we have an object capital B of scripty B and an object capital A of scripty A. Now, we're going to suppose that this functor here, scripty B of B comma R blank, is representable. So firstly, let me tell you what this functor here does. So we can think about this functor, scripty B of B comma R blank, as this kind of composition here. Okay, so we do this functor R from scripty A to scripty B, and then we just do this hom functor using our object capital B of scripty B. And that composition, making this triangle commute here, defines this functor here that I'm interested in. So you can kind of think of this as a kind of set theoretic representation of how this object capital B sees the stuff that comes into scripty B via R. Okay, yeah, this is our starting point. Now, this is going to seem kind of abstract to begin with, I guess, but I'm going to try and explain it, and we'll look at special cases, and hopefully, like, this setup is actually going to give you a clearer view of what universal morphisms are. So, here's our first bit then. We're going to suppose that basically this thing here is a representable functor. Okay, so we're going to suppose that we've got this natural isomorphism phi from this hom functor scripty A of A comma blank. So it turns out that this condition here is basically equivalent to having a universal morphism in general. Okay, so this is a very kind of powerful idea. Now, here's the way I think of this. Like, imagine that there's a entity in a different universe or something, right? And you want to understand it. Okay, so you're there in category B. You're there in category scripty B. You're a being called capital B, and there's this entity in another universe. You know, maybe it's like the particle laws that define this universe, or it's some angel or something that you want to understand, right? But you're here in this universe. So how are you going to understand what it's like for that other thing? Well, you have a set of things that you can interact with. Okay, so here you are, you're this object in this category scripty B. And you know that there are other objects around you, and there are sets of ways that you can relate to those objects. So in other words, you know the hom functor coming out of you, going to the other stuff. And suppose that there's a functor R from this other universe, scripty A, to your universe, scripty B. And so you can relate to the stuff that lands in your universe via R. Okay? And you can understand what it's like for this other entity if it happens to be the case that the set of stuff that entity interacts with, so when we have this hom functor scripty A of A comma blank, that's sort of a kind of set theoretic representation of the stuff that this angel A can interact with in its universe. Okay, so if you load in a Q, for example, you get the set of arrows from A to Q. That's a set. And sets are common notions in the angel's universe and in your universe. So you can relate those things. So basically, if it happens then that for any Q, the set of ways that the angel can relate to Q is basically equivalent to the set of ways that you can relate to where Q gets sent under this functor R. And that happens for every Q. And, we actually have like a natural isomorphism here. That kind of means that, you can use the kind of perspective of the angel to understand all about how you are going to see the stuff coming from this other world, coming from this other universe. Okay, this is I know this is maybe a daft example, but I'm just trying to illustrate kind of how I think of this stuff. So basically then what I'm trying to say is that the way that you, if assuming that you are B, the way that you see stuff that comes from R corresponds precisely to the way that the angel sees that stuff in the original category. That's how I interpret the existence of this kind of natural isomorphism here. And in a way, that's kind of why we say that this capital A is this sort of representing object for this kind of functor. Okay, that's kind of waffly, I know, but let's just take this mathematically now. So we're just saying that there's a natural isomorphism from this Hom functor here to this functor here. So what? Well, basically, it turns out that this condition here is really just equivalent to saying that we have this general kind of universal morphism. So I haven't gone over the definition of a universal morphism in this video. You can see my video on universal properties for the definition, but basically I'm saying that this condition here is equivalent to saying that capital A, this object of script here A, together with phi bar, where phi bar is the element corresponding to phi via the Yoneda lemma, well, these two things, A and phi bar together, constitute a universal morphism from capital B to this functor R. Okay, so this is really, really deep because it's basically giving us another way to think about universal morphisms. Now, another way that we can look at this, a kind of equivalent way to talk about universal morphisms, is to appeal to comma categories. And that's why I was defining comma categories earlier on. So another way to think about this kind of result here is to say that this is equivalent to saying that A, together with phi bar, give us an initial object of this comma category here, capital B comma R, or capital B slice R. And we can think of this as the comma category we get using these kind of functors here. So this is the big result. So now we sort of have three ways to look at universal morphisms. We can look at them as they were originally defined, through as these initial objects, which I've already discussed in the universal properties video. Now we have this new way of looking at them in terms of representable functors. And in fact, this phi bar here is what you might call a universal element. Okay, this is some new terminology. Okay, so one of the big ideas that we see coming up more and more now is this idea of universal morphisms. So I'm just going to quickly recap this idea of universal morphisms. Now, there's sort of a left-handed version of this and a right-handed version of it. And we're going to be looking at the sort of right-handed version today, but you can dualize all this stuff. So I'm going to be talking about a universal morphism from B, which is an object of our category scripty B, to R, where R is a functor which comes into our category scripty B from this category scripty A. And so this is the kind of thing that you could also call an initial morphism from B to R. So what is it? Well, it's a pair of an object A of scripty A and an arrow from B to R of A. And I'm going to call this arrow phi bar today. And this has to have this special sort of universal property. It has to have the property that for anything similar, so for any A dash, where there's an arrow from, where there's some arrow Q from B to R of A dash, there has to be this unique arrow H from A to A dash, such that if we lift H and we do it after phi bar, we get Q. Okay, this is just the definition of a universal morphism from B to R. And there are lots of examples of these kind of things, like initial objects and coproducts and co-equalizers. And we'll see later that natural number objects are examples of these kind of things as well. Now, I'm mostly interested in how this concept fits into this definition here. And you see here we have exactly this, that A and phi bar is forming a universal morphism from this object B to this functor R. And that happens if and only if A and phi bar together are forming the initial object of this comma category, B comma R. And if you want to understand why that's so, I mean, it's a good exercise to try and prove it for yourself, or you can look on my video on universal properties and I explain this in a bit more detail. But the main sort of point of this video is to say that these two conditions, which we sort of already understood were equivalent from previous stuff, also happen to be equivalent to this condition here. So basically what we're seeing with this big result here is that this kind of representation of this functor scripty B of B comma R blank, well, if we get that, and then we get the kind of thing that corresponds with that type of natural transformation under the Yoneda lemma. So, you know, we have this natural transformation from a Hom functor, which is phi, and then we can get this phi bar here, which is going to be an element of this functor here applied to capital A. So it's going to be an element of scripty B of B comma RA, or in other words, we can think of it as an arrow from B to R of A. Well, it turns out that that is a kind of universal element in the sense that when we pair it with A, it forms this initial object of our comma category. Or maybe a nicer way to think of it is that A paired with this phi bar gives us a universal morphism from B to R. But anyway, I'll probably put links to unlisted videos where I go through the proof of this result in the description to this video. Also, if you look in Tom Lienster's book on basic category theory, you'll find the sort of, the basic constituents of this proof in there. And you can look in Emily Riehl's book, Category Theory in Context. In chapter 2, you'll find the sort of seeds of the proof of this result there. So let's now use this result to understand the sort of thing I was alluding to before, which has to do with our special case of dynamical systems. So if you remember, we had this kind of funny result where if we look at the forgetful functor from the category of dynamical systems and we look at the elements category of that, we had that the initial object of that basically corresponded to 0 in this dynamical system of natural numbers. What's going on there? Right, so let's have a look at a special case now of this result, and hopefully we'll start to see the power of it. So what we're going to do is we're going to make some kind of simplifying assumptions. So we're going to use scripty B as being the category set, and we're going to suppose that capital B here is the singleton set. So we still have our functor R from A to B, but now we have this nice kind of simplification that happens because we're mostly interested in this functor scripty B of B comma R blank. But we know that scripty B is set, and we know that capital B is the singleton set. So what we have here is this hom functor from the singleton set to R comma blank. And a way that we can think of this is like what happens if we pick an object Q here. Well, then we're interested in the set of functions from this singleton set to R of Q. Well, that's going to equal the set that we get. Well, it's going to be isomorphic to the set that we get when we operate the functor R on Q itself, right? It's just the set of elements of R of Q, basically. And it turns out, in fact, that this functor singleton set comma R blank, as in this sort of hom functorish thing here, is naturally isomorphic to the functor R itself. So there's a natural isomorphism delta, and you can figure out the details behind that for yourself. But now let's have a look at our big result and what it looks like when we make these kind of assumptions here. So the first line's still the same when we say, oh, well, scripty B of B comma R blank is naturally isomorphic to a hom functor. But we know now that this thing on the right, we can write it like this now because of our assumptions. So it's set of singleton set comma R blank. And we know that this is naturally isomorphic to R. So we're going to have a natural isomorphism like this if and only if we have a natural isomorphism from our hom set to R itself. In other words, if and only if R is representable. Why? Well, because if we get this natural isomorphism, then we can compose it with our delta here. And if we have this one here, and if we have this kind of natural isomorphism, then we can compose it with the inverse of this delta here to get back to this. So yeah. So okay, these conditions are equivalent, but we already know now that this top condition is equivalent to saying that we have this initial object here. But we're assuming now that capital B is the singleton set. And so look what we get. What's this? It's our friend, the elements category of R. So there we have it. We have that basically R is representable, and it has this representation phi dash if and only if the elements that corresponds with phi dash, in other words, phi dash bar, the thing, so phi dash bar is the thing that corresponds with, so phi dash bar is the thing that corresponds with phi under the Yoneda lemma, and we're having that this forms an initial object of the category of elements if and only if the original phi dash gives us a representation of R. So basically, there's a correspondence between representable functors and these initial objects of our elements category. And we also know that any two initial objects are isomorphic to each other, right? This is one of the results we know. So this kind of proves that these kind of universal morphism here is going to be sort of defined up to a canonical isomorphism. And now also we know why this thing's called a universal element. And also now we know why this phi dash bar is called a universal element, right? Because what's this? It's an element of R of A, right? So what happens then in the particular case that we've been looking at? So in other words, what happens when scripty A is our category of dynamical systems, and what happens when capital A is our dynamical system of natural numbers? Well, basically in this case, we have that R is this forgetful functor. We know that it's representable. We know that it's represented by this dynamical system of natural numbers. So we have this. And therefore, when we find the kind of element of R of A, which corresponds with this natural isomorphism, well, this tells us that that's going to be an initial object of our category of elements of our forgetful functor, and that's exactly what we saw before. So, okay, I've shown that this big result demystifies what I was saying about 0 and the natural numbers. And incidentally, that defines what's called a natural number object. Okay, so if you look back now at the video I did on universal properties, I defined the natural number object there, and you can see that, you know, that's what we have. Another thing I was claiming though about this is it gives us a way to think about adjoint functors. And to see this, we can kind of see this intuitively if we just write down this central condition here, that this functor scripty b of b comma r blank is representable. Okay, so we'd probably write it like this. So let me just fill in this blank with something. Let's put a q in there or something. That's just a object that we can vary, so we'll suppose that it's equal to q. Now look at this. Does this remind you of anything? Well, what about if we had that a is equal to L of b for some functor L which goes in the opposite direction? So we have R that goes from A to B. What if we have a functor L from B to A? And what if A was equal to L of B? Well, in that case, this natural isomorphism looks like this. Now, does it remind you of anything? It should hopefully remind you of the definition of adjoint functors. L is the left adjoint to R if and only if we have this type of isomorphism, natural in B and Q. But we can kind of see like where this is coming from now, using this sort of result. Because what we're saying with this result is that for a particular B, we have that this kind of natural isomorphism here corresponds to the presence of a universal morphism here. By the way, these universal morphisms, I was also calling this kind of thing an initial morphism. Then there's the dual concept, which is called a terminal morphism. Anyway, what we can do now is just imagine that this kind of thing works for every object B in this category scripty B. In that case, there's a universal morphism from B to R for every object capital B, and that's exactly the condition that we need to be able to construct the left adjoint to this functor R. And so basically the way all this works, you can see now by this kind of condition, which I talk about roughly 2 hours and 18 minutes into my video on adjoint functors. And so basically what this is saying is that we're going to have a left adjoint L to our functor R, and we're going to have it precisely when we have a universal morphism from each B to R. And so this basically allows us to define how this functor L works up to isomorphism on objects, because these universal morphisms are defined up to isomorphism anyway, because they correspond to initial objects of the comma category, and initial objects are always sort of equivalent up to isomorphism. But how does it work on arrows? Well, basically, if you have an arrow G from B to B dash, then you can define L of G to be the unique arrow that makes this kind of square commute. So basically the idea then is that if you can find a representation of scripty B of R comma blank for every B, so for every B you find one of these A's, well then you can call that A L of B for every B, and you're defining a functor. So you just defined how that functor works on objects, and then if you just like get the natural isomorphisms that you have, do the Yoneda thing, you can get the corresponding universal morphisms, and then you can use this kind of result to finish building your left adjoint, because this tells you how to define how that left adjoint works on arrows. Right, so now let's return to our original problem. We want, if you remember at the beginning of the video, we said, okay, the thing we're going to focus on is we have the category of dynamical systems, and we have this forgetful functor R that takes it to set. And what we want to do is we want to determine the left adjoint of R. Now we're going to do this, and we're going to apply some extra sort of tricks. And these tricks work in quite general cases. Okay, so the only things we need for this is we need that this functor R is a functor from some category scripty A. For us, scripty A will be our category of dynamical systems, but it might as well be anything. And we want that this functor R is representable. Let's suppose that it has a representation capital A. The other thing that we need is we need that scripty A has all coproducts for this kind of argument that we're going to give. And this is the case for us. Okay, we know in our case of dynamical systems, we know the category of dynamical systems is a topos, and it has all coproducts. So the coproduct of a pair of dynamical systems, like say this one here and this one here, is basically just their disjoint union. So just put them together. So we have all coproducts, and yeah, we know that if we pick capital A to be this dynamical system of natural numbers, we know that that gives us a representation of this forgetful functor R. So we have what we need in this case. So let's now find the left adjoint of this functor R. It turns out that it exists in this case, so we're going to construct it. So let's go. So again, I'll restate our assumptions. We're assuming that R is a functor from some category scripty A to set. We're assuming that it's representable with representing object capital A and this natural isomorphism phi. And we're assuming that scripty A has all coproducts. Now, the first thing we're going to note is this very interesting relationship here. Okay, so let's just put a Q in here so we have something to point at. So what we're saying here is that the set of arrows in A from this coproduct of A with itself, B times, well, the set of arrows from this to Q is naturally isomorphic to a function which sends B to the set of arrows from A to Q. So let's just look at a special case of this, just to understand how this works, at least roughly. So let's take the case where B is just a 2-element set. Okay, so maybe it has 2 elements, I don't know, true and false, let's say. So in that case, what this object here is going to be is it's going to be the coproduct of A with A. And it turns out that an arrow from A plus A to Q is always going to be the kind of thing that you can write as a copowering of an arrow from A to Q called F with an arrow from A to Q called G. Because basically we always have this sort of diagram here. We have a first injection, a second injection, and here's F, and here's G, and then this is our sort of unique intermediary arrow here. And so it's the sort of universal property of coproducts that an arrow from A plus A to Q corresponds with a pair of arrows from A to Q, which corresponds with a function from this 2-element set to the set of arrows from A to Q. And this works more generally. So yeah, we have this kind of thing. Now, this kind of relationship here is what you call copowering or tensoring. So if you look on NLab on tensoring, you'll be able to read more about this kind of thing. But it turns out that we have this kind of natural isomorphism here because our category scripty A has all the coproducts. And so we can use this to our advantage, okay, because we're assuming that this functor R is representable. Well, we get this kind of isomorphism here, as I've said, because we have coproducts. And then we get this kind of isomorphism here because we have that R is isomorphic to this Hom functor here. So in particular, we have this kind of natural isomorphism phi here. And then if we just do set of B comma phi, using this kind of, lifting of arrows under Hom functor's notation, this gives us what we want. And so look what we end up with. We have that this is naturally isomorphic to this. Composing these natural isomorphisms gives us natural isomorphism. So what we have is this kind of thing. And this achieves our goal. How does it achieve our goal? Well, basically, we can define the left. Well, okay, let's put a Q in here for the blank so that it's easier to read. Now, let's just write this as L of B. And so essentially what I'm saying is we're defining L. So what I'm saying here is we're defining L of B to be this thing where we take the coproduct of A with itself, B times. And this is basically all we have to do. Now, let's just unpack this a bit more for the case of dynamical systems. So for dynamical systems, it turns out we can go even further. It turns out actually, in that case, we can write this even more simply as just B times A. And so what we end up with is that in the case of dynamical systems, because it has products as well, and the way that products work, we have that this kind of thing holds. And so we can just define L to be this functor which takes its thing and times it by A. But what is A here? Well, if you remember, what we were assuming is that A is this object which gives us this Hom functor which is naturally isomorphic to R. In other words, A is this representing object of our forgetful functor. In other words, in this case, A is our dynamical system of natural numbers. And so now we've solved our problem. So what this is saying is that the left adjoint of our forgetful functor, remember, our forgetful functor sends our category of dynamical, it sends a dynamical system to its set of states. And now we've figured out that the left adjoint to that, so if we have a set B, what is this functor doing? Well, basically it's going to be sending a set B to the kind of coproduct of the dynamical system of natural numbers, which is A, with itself B times. Okay, so we're going to have B copies of this thing all together. And that's basically what this left adjoint is doing. And so we've determined it. And basically what we've figured out is that the left adjoint of this, basically what we've figured out is that the left adjoint of this forgetful functor is this free functor that takes a set and then it forms a dynamical system that has this kind of, it has a copy of the natural numbers dynamical system for every element of that set, and it just sort of co-products them all together. Now, the end result might... Okay, so what I want to do just to finish is to show you how I remember this central result and also how we can get the dual to this result. So personally, I remember this adjunction formula. So I draw the adjunction so that we have the L is the left adjoint of R. I always draw it so that L points to the left. And then it's easy to remember this formula that lies behind the adjunction, that the left adjoint L goes on the left and the right adjoint R goes on the right. And then if we just take this formula and then we think, well, okay, I'm determining, let's say, the left adjoint. And then you say, well, let's write the left adjoint operating on B as A. Then we get the formula like this. And then if we just replace this Q here with a blank, then we have this formula here. And this is exactly the formula that we start with in this main result I've been talking about in this video. That basically scripty A of A blank has a natural, basically there's a natural isomorphism from scripty A of A blank to scripty B of B comma R blank. That we have this natural isomorphism like this. And then the claim is that when we have this kind of condition, that happens if and only if we have that A of phi bar is a universal morphism from B to R. And this basically corresponds to this kind of picture. And actually this phi bar is basically the same thing as the units in this adjunction. Because remember, we were thinking of this case where A is, if you like, equal to L of B. Okay, we're not really speaking about this left adjoint L here, but if we were, then we'd have that this morphism phi bar is of this kind of form, RLB, and this is actually what you'd think of in this case as the Bth component of the unit. But anyway, we've talked about this result a lot today, and we already know it's irrespective of how it connects. Well, I should say this result here, we've spoken about it a lot today, and we already know it irrespective of how it connects with the idea of adjoint functors, which it does in many ways. So how do we get the dual result? Well, again, we can start with our kind of adjoint functors formula here, but this time we just only want to involve the left pointing functor. So we replace RQ with something else, let's say B dash. And then we can get this kind of expression, making the B into a blank. We get that scripty A of L comma, we get that scripty A of L blank comma Q is going to be naturally isomorphic to B of blank comma B dash. And basically, if we just think about what would happen in this adjunction and what would be the role of the co-units, we can see that it makes sense that there should be such a natural isomorphism like this, if and only if we have that B comma phi bar, where phi bar is the element of this corresponding with our natural isomorphism under the Yoneda lemma. Well, we're going to have that this natural isomorphism exists if and only if B dash comma phi bar is going to be a natural isomorphism from L to Q. And so this is the sort of dual result to the result which I've been speaking about for most of the video. And basically this result up here, which I've been speaking about for most of the video, as in this statement, basically allows us to understand what a universal morphism from an object to a functor is in terms of representable functors, but there's a dual result which happens when we want to understand the nature of universal morphisms that go from functors to objects, the so-called terminal morphisms. And this is the dual result then that we want. So this is the sort of other side of the coin of what we've been discussing for most of this video. So basically this result allows us to find our universal morphisms which go from functors to objects, the so-called terminal morphisms, whereas this other result that we've been looking at previously allows us to understand the kind of initial morphisms in terms of covariant representable functors. So basically this gives us initial morphisms in terms of covariant representable functors. This gives us terminal morphisms in terms of contravariant representable functors. And you can basically get both of these results by taking this kind of adjoint functors formula here. The usual way I remember this stuff is I write my adjoint functors like this, with L pointing to the left and R pointing to the right, and then we get this, where the L's on the left and the R's on the right. And then if we replace the R of Q with B dash and the B with a blank, we get this. And then we see that the kind of co-unit of this adjunction ends up looking like this. And similarly, the result we've been looking at previously, you can get by working the other way around.